Welcome back to the deep dive. Today, we are tackling a question
Yeah.
that is, it's so fundamental it affects every single moment of your life.
It really is.
Why does time have a direction? Why does it only go forward?
Uh-huh.
We're going to take this, this abstract concept of irreversibility,
Yeah.
the arrow of time, and we're going to ground it
Ground it on what, though?
in cold, hard mathematics, specifically the mathematics of chance.
That's right. Our mission today is a deep dive into the concept of entropy. You'll see it written as a capital S.
Right.
And we're going to move from that simple observation that, things seem to happen in one direction to the incredibly elegant statistical mechanics that Ludwig Boltzmann came up with.
And his work explains, with what feels like absolute mathematical certainty, why that forward direction is, for all intents and purposes, mandatory.
Statistically mandatory? Yes, that's the key.
Okay, so let's unpack the core paradox right away.
Right.
Because it's something everyone, and I mean everyone, experiences daily. Think about your morning coffee. You make it piping hot, you set it on the counter, and what happens? It cools off. It always reaches room temperature.
Right. We just accept that as natural.
But here's the paradox. According to the first law of thermodynamics, the law of conservation of energy, there's nothing, energetically speaking, wrong with the reverse.
You mean the cold coffee spontaneously getting hot?
Exactly. Pulling stray heat out of the cup, out of the air around it, and concentrating it back into the liquid, energy would still be conserved.
The total amount of energy in the room stays the same, whether the heat flows out of the coffee or flows back in. The first law is perfectly happy either way.
But you have never, ever seen that reverse process happen.
Never. A cold drink doesn't suddenly boil itself by stealing heat from the table. It's absurd to even think about.
And that inability for the process to just run backwards, that's the profound central problem of thermodynamics.
The first law is totally directionless. It governs the quantity of energy, but it has nothing to say about the direction of a process. It allows everything to run forwards or backwards.
And yet, our entire existence tells us that some processes are, they're a one-way street. They're strictly forbidden from reversing on their own.
So we desperately need something new, a new physical quantity that governs the direction, not just the amount. And that quantity
Is entropy, capital S.
That's the one.
So the idea here is that nature has this built-in directionality. And to help us visualize why this exists, our source material sets up, I think, the perfect thought experiment.
Oh yeah, the gas expansion. It's a classic for a reason.
Walk us through it.
Okay, so imagine a container, a simple box, and it's divided exactly in half by a removable barrier, or maybe a wall with a little valve in it.
Got it.
We begin in what we'll call state A. We pump a gas, let's say nitrogen, entirely into the left half of the container.
And the right half.
A complete vacuum, nothing there.
So state A is the epitome of order. All particles are neatly contained on one side.
Exactly, maximum order. Then you open the valve. Or you just pull the barrier out. What happens?
Whoosh. The gas rushes out and fills the entire container.
Instantly. It distributes itself more or less evenly throughout both halves. That's our state B. And that transition from A to B, it's spontaneous, it's voluntary, and it happens incredibly fast.
The natural progression is always towards filling all the available space.
Right. Now, here's the big question. The cosmic joke, really. Once you're in state B, the gas is all spread out. What is the chance that at some point all those gas molecules will suddenly and spontaneously decide to go back?
To just retreat into the left half? Recreating state A, leaving the right side a vacuum again?
Yeah.
That's scientifically absurd. If that happened in this room right now, we'd certainly be suffocating in a vacuum while all the air huddled in that corner over there.
It's a terrifying thought. But again, if the gas just moved from B back to A, no work is done, energy is conserved, the first law is totally fine with it.
So why does it never, ever happen?
Well, the initial intuitive conclusion, and the one we're about to spend this whole deep dive quantifying, is actually quite simple.
State B is just more probable.
State B, the distributed chaotic state, is simply more probable.
So the arrow of time isn't some mysterious cosmic force. It's the universe playing the odds.
It's a game of statistical chance, played with an unimaginable number of dice.
Our mission, then, is to figure out exactly how much more probable that messy state is, and how that quantification becomes the rigorous definition of entropy itself.
Let's do it.
To quantify probability, we have to start by defining what we're counting. And this brings us to a really crucial distinction that's at the very foundation of statistical mechanics.
Yes. We have to be incredibly precise about what we mean by the word state in physics.
It's not as simple as it sounds.
Not at all. We have to differentiate between the microscopic view and the macroscopic view. Let's start with the microstate.
Okay.
The microstate is the ultimate detailed configuration of the system. I mean, imagine you could freeze time and take a perfect snapshot of every single atom. The microstate is knowing the precise location, the velocity, the orientation of every single particle. It's knowing, okay, particle 1 is on the left, particle 2 is on the right, particle 3 is on the left, and so on, for all of them.
That sounds exhausting. For a mole of gas, that's knowing where every single one of those 10 to the 23 particles is at a specific instant.
It's the specific hand that the universe deals us at any given moment. It's the ultimate level of detail.
Okay, so that's the microstate. What's the macrostate then?
The macrostate is what we can actually measure in the real world, in bulk.
The big picture stuff.
Right. It's defined by observable, measurable properties. Things like the total pressure, the temperature, the volume. Or, in our gas example, it's as simple as saying, there are $1 particles on the left side and $2 particles on the right side.
Ah, I see. So the macrostate is the overall result we see. The thermometer reads 20 degrees Celsius. The microstate is the almost infinite number of ways the individual molecules could be zipping around to give us that 20-degree macrostate.
That is the key connection. And this is where we introduce the concept of statistical weight, or multiplicity. It's denoted by the Greek letter omega.
The big omega.
And omega is simply the number of possible microstates that all correspond to a single specific macrostate.
So it's a counting problem.
It's purely a counting problem. It's like calculating the number of ways you can get a specific hand in poker or the odds in a lottery drawing.
And for our gas example, with the box split into left and right, we can actually calculate this using the binomial coefficient formula.
That's right. If you have n total particles, the number of ways to choose n dollar of them to be on the left is n factorial divided by n dollar 1 factorial times $10 2 factorial.
Okay, that's a bit abstract. Let's ground this with the simplest possible example from our source material.
The 4-particle system. Let's say n equals 4, just 4 particles.
And let's compare the two crucial macrostates. Macrostate A, the perfectly ordered state. All 4 particles are on the left side.
Okay, so n dollars equals 4, 2 inos or equals dollars. How many microstates can give you that result?
Well, there's only one way. Particle 1 has to be on the left, particle 2 has to be left, 3 left, and 4 left. That's it.
The counting is easy. Omega is just 1. There's only one possible configuration for perfect order.
That's our starting point, right? The state of minimum probability.
Exactly. Now, for macrostate B, this is the state of, let's call it maximum disorder. Or, more accurately, equal distribution.
So 2 particles on the left, unadult 1 equals 2, and 2 on the right, 22 equals 2.
Now, how many microstates can produce this 22 macrostate? You have to choose 2 particles out of the 4 to be on the left side.
Using the formula, that's 4 factorial, which is 24, divided by 2 factorial times 2 factorial. So 24 divided by 4, that's 6.
6. There are 6 different ways. It could be particles 1 and 2 on the left, or 1 and 3, or 2 and 4. You get the idea. There are 6 distinct microstates that all look from the outside like the same 22 macrostate.
So 6 ways to be distributed versus only 1 way to be perfectly ordered. The equally distributed state is 6 times more probable than the ordered state. Even with just 4 particles, chaos is already a significantly better bet.
It is. But you're right to be a little skeptical. 6 times more probable doesn't explain why a room full of air doesn't just spontaneously cluster in a corner.
Yeah, 6-to-1 odds are good, but I'd still see it happen now and then. This isn't a guarantee of certainty.
You're absolutely right, and that brings us to the mathematical crescendo of the whole argument. The profound, unbelievable difference that happens when we scale up.
When we go from 4 particles to the real world.
Right. Where we're not dealing with 4, but with Avogadro's number, n, which is roughly 10 to the 23rd particles for a single mole of gas.
And suddenly the difference in probabilities is no longer 6-to-1. It becomes, well, truly astronomical.
The scale is the entire game here. When you start trying to calculate with factorials of that size, like 10, 20 factorial, you just can't.
It's nothing you can plug into a calculator.
Yeah. No standard computer, not even a supercomputer, can handle it. The numbers are simply too large to express, let alone calculate precisely.
So what's the workaround? How do physicists deal with this?
We have to use powerful mathematical approximations. The main one here is called the Stirling formula.
Okay.
It's a clever trick that tells us for very, very large numbers n, the natural logarithm of n factorial is approximately n times the log of n minus n.
So it turns a discrete counting problem with factorials into a continuous function with logarithms.
Precisely. And that tool is absolutely essential just to handle the sheer scale of the numbers involved in thermodynamics.
All right, let's take that power tool and apply it to our two extreme states again. But this time, let's use the big number, n $10 particles.
Okay. The macro state of maximum probability is the equal distribution, right? $1 equals $10 equals n divided by 2.
Right.
The statistical weight, omega, for that state, it turns out, is approximately 2 to the power of n. So for n equals 10 to the 23rd, omega is 2 to the power of 10 to the 23rd.
Let me just pause there. 2 to the power of 10 to the 23rd. That's a 2. Followed by a number of zeros that is 100 million billion. Billion.
Yeah.
How do you even begin to grasp a number that big?
You don't really. It's genuinely difficult. For comparison, people estimate that the total number of atoms in the entire observable universe is around 10 to the 80.
Okay, 10 to the 80, that's a 1 with 80 zeros.
Our omega, for a single puff of gas in a box, is 2 to the power of 10 to the 23rd. The number of possible configurations for that one little bit of gas is so much larger than the number of atoms in the universe that the comparison becomes meaningless. It's beyond hyper-astronomical.
And what about the other state? The macro state of minimum probability, where all the particles suddenly go back to the left side. The perfectly ordered state, what's its omega?
It's still just 1.
Wow.
There is only one way to achieve perfect order.
So the ratio of probabilities, the likelihood of the gas being evenly spread out versus the chance it's all in one corner, is 2 to the power of 10 to the 23rd.
Okay.
To 1.
Yes. And that factor isn't just large, it's statistically dominant in a way that dictates physical law.
This is what fundamentally explains irreversibility.
It's the whole story. We don't say the gas cannot retreat to the ordered state. We say the probability of it doing so spontaneously is so infinitesimally small
that it just won't happen.
You'd have to wait, 10 to the power of 10 to the 23rd times the age of the universe for it to happen, and you would almost certainly still be wrong.
The overwhelming number of ways to be disordered means the system just has to, on average, find one of those disordered states. It can't miss.
And the statistical certainty leads us directly to Boltzmann's famous definition of entropy.
The equation you see on every physicist's t-shirt.
That's the one. S equals K sub B times the natural log of omega. S equals take log n omega.
Okay, let's break that formula down. S is entropy, we know that. Omega is the number of microstates, our count of chaos. But why the natural logarithm, Ln? And what's that little constant, the Boltzmann constant?
The logarithm is there for deep mathematical reasons that we'll get into, but for now, you can think of it as a way to make the numbers manageable and to make entropy additive, which is important.
Okay, we'll put a pin in that. What about Kelly v. Day?
To me, Kelly v. Bulls is the most fascinating part of the formula. It's essentially a unit conversion factor.
A unit conversion factor, like converting inches to centimeters.
In a way, yes. When we calculate the natural log of omega, what we get is a pure dimensionless number. It's just a measure of counting of information.
Right.
But classical thermodynamics, the kind developed in the 19th century, defines entropy in measurable units related to energy and temperature, specifically joules per Kelvin.
So Kelly-Bowles is the bridge.
It's the essential bridge. It connects the purely statistical, microscopic world of counting particles to the macroscopic, measurable world of heat and temperature. It turns the number of choices, Ln omega, into a thermodynamic quantity S that an engineer can actually measure.
That reframes the entire equation for me. So entropy isn't just some vague measure of disorder. It's a direct logarithmic measure of the number of ways a system can possibly exist.
Exactly. If S is high, it means omega is huge, which means there are countless ways the system could be configured at the microscopic level.
Which is why you also said it's a measure of our ignorance about the exact microstate.
Precisely. If a system has high entropy, there are so many accessible microstates that we have no realistic hope of ever knowing the exact one it's in.
But if it has low entropy, omega is small. There are very few ways it can exist, and so we have a lot more information about its specific configuration.
Right.
So the second law of thermodynamics, the famous statement that the entropy of an isolated system can never decrease, is just the universe obeying the most basic rule of probability.
That's it. Systems spontaneously tend towards states of maximal probability. That means max L omega. And because of the logarithm, that means maximal entropy.
It's just probability masquerading as a physical law.
And we can see just how rigid this statistical certainty becomes when we look at a graph of the probabilities. The sources call this the sharpness of probability.
Right. They use the binomial distribution, which looks like a bell curve, to show how often a certain split between left and right occurs.
For a small number of particles, like our n equals 10 example, the distribution is pretty broad. The graph showing the probability of getting a 55 split versus, say, a 37 split is relatively flat.
So fluctuations are common. You'd expect to see a 37 split pretty often.
All the time. But as n grows, that graph changes dramatically. It gets taller and it gets incredibly narrower. The peak right at the center at the n2 equal distribution becomes impossibly sharp.
Like a needle.
For n equals 1,000 particles, which is still a tiny number, the peak is already so sharp that any macrostate deviating even slightly from the 500-500 split becomes exponentially improbable.
And there's a mathematical reason for this. The relative width of this probability distribution shrinks in proportion to 1 over the square root of n.
That is the key mathematical insight.
So if n is enormous, like $1023, the square root of n is still huge, but 1 divided by that number is
Vanishingly small. It means that for any macroscopic system, anything you can see or feel, the width of that peak is effectively 0.
So we only ever observe the one macrostate that corresponds to the maximum probability.
The exact center of the distribution. This mathematical certainty is what makes the macroscopic world appear so deterministic and stable, even though it's built on random chaos.
So we've basically confirmed that the second law of thermodynamics is a statistical law. It applies to systems with huge numbers of particles. But if we could zoom into the nanoworld, do these laws still hold?
Not strictly, no. And the timescales provided in the sources really highlight this difference between the microscopic and macroscopic reality.
Okay.
Think about a tiny, tiny volume, a single nanocubic meter of gas. It's far smaller than the eye can see. Inside that volume, the microstates are changing at an incredible speed.
How fast?
Approximately 10 to the 12 times every single second.
1 trillion changes per second.
1 trillion times a second, it's in a new configuration. So let's ask the critical question. In a system that small, how long would you have to wait to see a really severe fluctuation, like all the particles clustering on one side?
We did the calculation for 4 particles, and the chance was 1 in 16.
Right. Now, if you only have 10 particles in that little box, the waiting time for them to randomly all cluster on one side is about 10 to the minus 9 seconds.
A nanosecond.
It happens constantly. This is why in the nano world, strict thermodynamics just doesn't apply. The system is constantly and violently fluctuating between high and low entropy states.
So if you're a biologist studying a process that only involves, say, 10 protein molecules, you can't rely on these laws in the same way.
Absolutely not. But the moment we scale up, the picture changes completely. And it's all because of that brutal 1 over the square root of n narrowing of the probability peak.
So what happens at 100 particles?
With just 100 particles, the waiting time for them all to cluster on one side jumps to 10 billion years.
Wow. That's roughly the age of the universe.
That's the crossover point. 100 particles is enough to guarantee stability over cosmological timescales.
And at 1,000 particles.
At 1,000 particles, the waiting time is 10 to the power of 280 years.
No, I can't even.
To put that number in perspective, if every single atom in the entire known universe ran a parallel simulation of this gas experiment, from the Big Bang until today, not a single one would be expected to see that fluctuation occur.
It's an unimaginable number.
It's utterly beyond imagination. And this is why we say the second law isn't a strict prohibition. It's a statistical certainty for any large system.
The sources even give the probability for a much smaller fluctuation, like a 10% density difference.
Right, 10% more particles on the left than the right. For 100 particles, that happens all the time. The probability is 0.6.
But for 10,000 particles, which is still a tiny system,
the probability plummets to 10 to the minus 22. That kind of measurable density fluctuation will simply never, ever occur in a macroscopic volume of gas.
And that provides this beautiful, intuitive explanation for why the air in this room seems perfectly uniform.
Even though the molecules are flying around chaotically at thousands of miles per hour?
The statistics of large numbers just smooth everything out.
Yeah.
It creates the stable, predictable, macroscopic world we all rely on.
So to synthesize this whole statistical concept, S equals K sub B times the log of P, where P is proportional to omega, means that entropy is a direct measure of probability.
And the drive to equilibrium is just the drive to maximize that probability.
Systems move from ordered, low-entropy states, which are incredibly unlikely, to disordered, high-entropy states, which are statistically inevitable. And for an isolated system, the rule is rigid. Entropy can never decrease.
Okay, we have established this rigorous statistical foundation for the arrow of time, but now we have to face a really crucial challenge, both historically and conceptually. For decades before Boltzmann and his particle counting, scientists were already using a totally different definition of entropy, one based on heat flow.
That's right.
So now we have to show that this super abstract particle counting statistical definition is mathematically consistent with the classical measurable definition that came before it.
And this bridge isn't just some academic exercise. It's really the unification of the microscopic and macroscopic worlds.
It's the proof that they were talking about the same thing.
It proves that whether you look at a system from the outside, with a thermometer, or from the inside, by counting atoms, you arrive at the exact same physical reality.
Let's go back for a second to the structure of Boltzmann's equation.
Yeah.
S, kcalibel, ln omega. We put a pin in the logarithm, but let's really dig in now. Why the logarithm? Why not just use omega directly?
The reason lies in a crucial requirement of classical thermodynamics, and that is that entropy must be an extensive quantity.
Okay, what does extensive mean in this context?
It means that the property scales linearly with the size of the system.
So if you double the system, you double the property.
Exactly, like mass or volume. If you take two identical systems, say box 1 of gas and box 2 of gas, and you combine them into one bigger system, the total entropy has to be additive. It's just S total equals S1 plus S2.
That makes perfect sense. The total amount of chaos should be the sum of the chaos in the parts.
It feels intuitive, right? But now look at the statistical nature of omega, of probability. When you combine two independent systems, the total number of microstates is multiplicative.
Right. If you have two coins, the number of outcomes is 2 times 2, which is 4. Probability multiplies.
Precisely. If system 1 has omega 1 possible configurations and system 2 has omega 2, the total number of combined outcomes is omega total equals omega 1 times omega 2.
So we have a problem. We have a physical requirement that entropy has to add, but a statistical reality that the number of possibilities has to multiply.
We do. So we need a mathematical function that can take the product of two numbers and turn it into the sum of those two numbers.
And that function is the logarithm.
It's the unique property of the logarithm. Boltzmann shows it specifically because the log of omega 1 times omega 2 is mathematically identical to the log of omega 1 plus the log of omega 2.
It's just a perfect piece of mathematical tailoring to make the two worlds fit.
It forces the statistical definition to align perfectly with that classical requirement that entropy be extensive and additive.
Okay, beautiful.
Yeah.
Now let's pivot back to that classical side in detail.
Yeah.
The definition that was formulated by Rudolf Clausius back in the 19th century.
Right. Clausius defined the change in entropy, ds, as the amount of heat supplied, which he wrote as delta Q, divided by the absolute temperature, T.
So ds equals delta Q over T.
But there's a huge catch. It's delta Q sub rev. The rev stands for reversible.
And why must the process be reversible? What does that even mean?
It's a really important constraint. A reversible process is a theoretical ideal. It's a process that's performed infinitely slowly, so the system is always in perfect equilibrium at every single step. It represents the most efficient way to transfer energy. If the process is irreversible, like our gas rushing wildly into a vacuum, some of that energy change is, wasted or dissipated as turbulence, and you can't use the actual heat exchange to calculate the entropy change. It just doesn't work.
And this is where the classical definition hits a conceptual wall,
right?
When we try to apply it to our central thought experiment, the free, irreversible expansion of gas into a vacuum.
It absolutely does. Remember, when the gas just rushes into the vacuum, it's not pushing against anything, so it does zero work.
Right.
And if the container is insulated, it exchanges no heat with the surroundings. So delta Q is 0.
So if we just blindly applied Clausius's formula, we'd get that delta S is 0.
Which we know is wrong. We know intuitively, and we've proven statistically, that this is a spontaneous, irreversible process. Entropy must increase.
So the classical definition only really works for these imaginary, perfect, reversible paths.
Correct. But the saving grace is that entropy is a state function.
Meaning it only depends on the start and end points, not the path you took to get between them.
Exactly. So to calculate the entropy change for any real, irreversible process, we have to ignore the actual messy path it took. Instead, we invent a hypothetical, reversible ersatz path, A substitute path that starts at the same initial state and ends at the exact same final state.
And because S is a state function, the entropy change along this imaginary, easy-to-calculate path has to be the same as the entropy change for the real process.
It has to be.
So what would be the reversible equivalent for our gas expansion?
The reversible equivalent would be an isothermal expansion.
Okay, what's that?
Instead of a vacuum, we put a frictionless piston there. Then we let the gas expand very, very slowly, pushing the piston and doing the maximum possible amount of work.
And isothermal means we keep the temperature constant.
Right. To keep the temperature from dropping as the gas does work, we have to continuously supply a little bit of heat, Q, from an external heat bath.
So the initial state volume V1, temperature T, and the final state volume V2, temperature T, are identical for both the real path and this imaginary path.
Which means the calculated delta S must be identical for both.
That is a brilliant conceptual move. You just sidestep the messy reality. Okay, let's get to the mathematical payoff, the proof of consistency. We need to calculate delta S both ways for doubling the volume of an ideal gas.
Let's start with the classical calculation. We're using our ersatz path, the reversible isothermal expansion.
Right.
Now, for an ideal gas, the internal energy, U, only depends on its temperature. Since the temperature is constant isothermal, the change in internal energy is 0.
Okay, delta U is 0.
So according to the first law of thermodynamics, the heat we supply, Q, must exactly equal the work, W, that the gas does on the piston.
So all we need is the formula for the work done during this process.
And that work is given by W equals N times K sub B times T times the natural log of V2 over V1.
Okay, and since Q equals W, the heat we added is the same amount.
Exactly. Q equals NKBT ln N of V2 over V1.
Now we just plug that into Clausius's definition for the entropy change. Delta S equals Q divided by T.
We take that whole expression for Q and we divide by T, and you can see the temperature terms, the T in the numerator and the T in the denominator, they just cancel out.
Leaving us with the classical entropy change. Delta S classical equals NKB times the natural log of V2 over V1.
And for our specific example, where we double the volume, V2 equals 2 times V1.
So the log of V2 over V1 is just the log of 2.
Delta S classical simplifies perfectly to N times K sub B times the natural log of 2. That's our classical answer, derived entirely from macroscopic ideas of heat and work.
Okay, the bar is set. Now let's do the same calculation using Boltzmann's statistical definition.
Statistically, we're not thinking about heat, we're thinking about probability. When we double the volume of the container, what happens to the number of available positions for each particle?
It doubles.
And since the particles are independent, the total number of microstates for the final state compared to the initial state increases by a factor of 2 to the power of n.
The probability ratio, P2 over P1, is 2 to the n.
Right. Now, the change in statistical entropy is the final entropy minus the initial entropy, S2 minus S1.
Which, using S equals KB ln P, becomes KB ln P2 minus KB ln P1.
And using the properties of logarithms, that simplifies to KB times the log of the ratio, P2 over P1.
So we plug in our probability ratio of 2 to the n. Delta S statistical equals KB times the natural log of 2 to the n.
And here's the last step. There's another fundamental property of logarithms that says the log of a number to a power is the same as the power times the log of the number.
So we can pull that n out front.
We pull the n out front and we get
Delta S statistical equals n times KB times the natural log of 2.
It is the exact same result.
Wow.
NKB ln 2. The increase in entropy you calculate by counting microscopic configurations, atom by atom, is mathematically identical to the increase you calculate by measuring macroscopic heat flow in an imaginary process.
The elegance of that is, it's really remarkable. You're linking a macro measurement like heat flow to a statistical count of atoms.
It proves that the laws of classical thermodynamics, which were really born out of the engineering needs of the 1850s, are perfectly explained and justified by the statistical chaos of 10 to the 23rd particles.
This consistency just confirms, without a doubt, the statistical foundation of the arrow of time. It's not two different ideas, it's two sides of the same coin.
That's a perfect way to put it.
Okay, so we spent a lot of time establishing why systems move toward higher entropy. Now, let's talk about where they stop. When does the universe finally find rest, and what dictates that final state? This brings us to equilibrium.
Right. A system is, by definition, at equilibrium when its macroscopic properties, its pressure, its temperature, its density, they're just no longer changing over time. It's settled down.
And for the simplest possible case, the completely closed system.
The one that's totally isolated from the rest of the universe, meaning its internal energy, U, and its volume, V, are fixed and can't change.
For that system, the rule is simple.
Entropy S must be maximized.
Maximum chaos. The system has explored all of its possible microstates, and it's settled into the configuration that has the highest statistical weight, the biggest omega.
Correct. So at equilibrium, any tiny hypothetical change in entropy ds away from that maximal state has to be zero. The system is at the very peak of the probability mountain, and there's just no statistically advantageous move left to make.
This sounds straightforward, but as you mentioned earlier, this isolated system is an idealization. It's not how we typically interact with matter.
No, we don't live in a perfect thermos flask.
Okay.
And this is where we have to transition to the complexity of the real world, opening the system.
Right.
Most processes we actually care about, a chemical reaction in a lab, ice melting in a glass, a biological process in a cell, they are not isolated.
They're usually held at a constant temperature by their surroundings, or at a constant pressure because they're open to the atmosphere.
Exactly. So we have to look beyond just the little system we're studying. We have to remember the global requirement for the second law.
That the total entropy of the system plus its surroundings must always increase or stay the same.
ds total must be greater than or equal to zero. This is absolutely vital.
Why is that so important?
Because it means that the entropy of our small system of interest, let's say a beaker of salt water that's crystallizing, that local entropy can actually decrease.
Which seems like it violates the second law.
Yeah.
Crystallization is creating order, right?
It is. It's the creation of a highly ordered structure, which means a big local reduction in omega, and therefore a local reduction in S.
But it doesn't violate the law.
It doesn't, because the act of forming that crystal releases heat into the much larger surrounding environment, like the air in the room. And that heat increases the disorder, the entropy of the surroundings by an amount that is guaranteed to be greater than the decrease of entropy in the crystal itself.
So the overall global entropy still goes up. The universe gets messier, even if one tiny spot gets tidier.
Exactly. The fundamental law is satisfied. But you can imagine constantly having to track the system and the entire universe is, well, it's impractical.
We need a simpler scorecard. Something internal to the system that tells us if a process is going to be spontaneous, given the external constraints, like constant temperature or pressure.
This need is what leads us to derive the thermodynamic potential functions. We create these new functions from the first law and that maximum entropy principle. And they essentially capture the system's drive toward global stability, but they do it by minimizing a specific property within the system itself.
Okay, so let's examine the first of these. The role of Helmholtz free energy, which is a capital F.
Right.
What are the specific boundary conditions that make F the right tool for the job?
We use Helmholtz free energy when we hold the temperature, T, and the volume constant. The classic example is a reaction happening inside a bomb calorimeter, a rigid, sealed steel vessel that's submerged in a massive water bath.
Volume is constant. Temperature is constant. Now, the definition of this potential is F equals U minus TS. Why does the system want to minimize F?
Because F represents this delicate competition, a trade-off between two opposing drives inside the system.
Okay, what are they?
The first drive is to minimize the internal energy, U. This is often the system's natural tendency towards mechanical stability. Think of a ball rolling down a hill to lower its potential energy. Systems like to be at low energy.
And the second drive?
The second drive is that minus TS term. We know S, entropy, always wants to be as big as possible. It wants to maximize.
Right.
But because there's a minus sign in front of it, to make F as small as possible, the system has to make S as large as possible. So it's also driving the system towards maximum entropy.
So it's a tug of war. The system is trying to find the lowest energy configuration, the most stable state, while at the same time trying to find the most chaotic, high entropy configuration.
And the final stable state, the equilibrium, is the perfect compromise between those two opposing objectives.
And the weighting factor, the thing that decides which drive wins that tug of war, is just the temperature T.
T is the crucial arbiter. At low temperatures, T is small, so the minus TS term doesn't contribute very much to F.
So F is basically just equal to U.
Roughly, yes. Therefore, the drive for minimal internal energy wins. Systems stabilize by forming highly ordered, rigid structures like solid crystals, where the strong chemical bonds minimize U order prevails.
But if we crank up the heat, the temperature T becomes large. And suddenly that minus TS term becomes the most important part of the equation.
It dominates the entire expression. And now the drive toward maximal entropy wins. At high temperatures, the system is totally willing to dramatically increase its internal energy by melting, by boiling, by breaking bonds, just to gain a huge increase in disorder, because that's what will minimize the overall value of F.
So a phase transition like melting is just the system jumping to a new state that minimizes F under the new, hotter temperature constraint.
That's a perfect explanation of it. But as we noted, F is for constant volume, which is pretty restrictive. We need the potential that's more relevant to everyday chemistry and biology.
And that would be the chemist's choice. Gibbs-free, enthalpy, capital G.
Yes.
What are the conditions that make us use G?
Constant temperature, T, and constant pressure, P. This is the most practically relevant potential because it describes almost everything we care about. A reaction in an open beaker in a lab, a process in a biological cell.
It's constantly exposed to atmospheric pressure, and it's usually maintained at a constant temperature. Now, the definition of G is G equals U plus PV minus TS, or more commonly, G equals H minus TS, where H is enthalpy. Where does that extra PV term come from compared to F?
It comes from the fact that we're no longer at constant volume. We've switched to constant pressure. So if the volume is allowed to change during reaction, the system might have to do work on the atmosphere to expand.
Or the atmosphere does work on it to compress it?
Right. That's the PV work. So enthalpy H is defined as the internal energy plus the energy required to make room for the system at that constant pressure.
So Gibbs-free enthalpy is the potential that counts for everything. The internal competition between energy and entropy, and the fact that the system might change volume and do work on its surroundings.
It's the whole package.
Yeah.
And the crucial output for any process is the change in Gibbs free enthalpy, delta G. The system always strives toward the minimum of G.
And this is the definitive scoreboard for spontaneity in the real world.
It really is.
If delta G for a process is negative, the reaction proceeds voluntarily. It's spontaneous. If delta G is positive, the system can't get there on its own. You have to put energy in to force it to run uphill.
This is why Gibbs free enthalpy is often called the useful energy. It's the part of the system's total energy that's actually available to do work, like forming a new chemical bond or running a biological motor under these standard conditions.
It's what drives life. It's what drives all of chemistry. And its sign tells us the arrow of time for that specific local process.
You got it.
Okay, we've covered 4 key scenarios now. Let's just quickly systematize them. Let's review when a system truly finds rest, its equilibrium state, which depends entirely on the constraints we put on it.
All right, 4 key criteria, each corresponding to minimizing a different potential function.
First, the truly isolated or adiabatic system. Fixed internal energy, U, fixed volume V.
That system maximizes entropy, S, or equivalently, it just minimizes its internal energy, U. It's the simplest case.
Second, constant temperature T and constant volume V, the sealed flask in the water bath.
That system minimizes the Helmholtz free energy, F. It's the balance between energy U and the entropy drive minus TS.
Third, constant temperature T and constant pressure P, the open beaker on the lab bench, the chemist's choice.
That system minimizes the Gibbs free enthalpy G. This is the gold standard for predicting chemical spontaneity.
And finally, the fourth case, one that often comes up in engineering, constant pressure P and adiabatic, meaning no heat is exchanged.
That system minimizes the enthalpy, H. This governs processes like gas flowing through an insulated pipe, where the volume can change but no heat gets in or out.
What a synthesis. We started by noticing that a cold coffee never spontaneously gets hot, and we've ended up with this rigorous statistical framework that dictates the rules for every chemical reaction, every phase transition, every biological process on Earth.
We really have. We've mathematically unified the chaotic microworld with the predictable, stable macro world.
We truly have connected that observable direction of time, the deep mystery of irreversibility, to the simple fundamental mathematics of just counting particles.
And we saw how the chaos of individual atoms, specifically the overwhelming statistics of 10 to the 23rd microstates, creates these rigid, predictable laws that we call thermodynamics in the macroscopic world.
And I think most powerfully, we demonstrated that this statistical understanding, S equals KEB ln omega, is perfectly mathematically consistent with the old classical definition, ds equals delta Q rev over T.
The simple measurement of heat flow confirms the complex counting of trillions upon trillions of particles. It really is a stunning achievement of physics.
We saw how this drive towards statistical maximization naturally leads to the creation of these potentials, F and G.
Right. These potentials let us predict spontaneity and stability under real-world, non-isolated constraints. They translate the universal mandate of increasing entropy into local, functional rules for chemistry and for life.
And here's where it gets, I think, really interesting based on the definitions we just covered.
Okay.
We noted that for chemists, a negative delta G, the ultimate sign for a spontaneous reaction here on Earth, where temperatures are relatively moderate, around 300 Kelvin.
Right.
But let's take that temperature weighting factor and push it to its absolute limit.
Remember that both the Helmholtz and Gibbs potentials have that crucial minus TS term. Temperature, T, is the weight that balances the system's tendency toward low energy, U or H, versus high disorder, S.
So what might happen to chemical processes, or any physical process, deep inside a star? Or in other parts of the universe where the temperature, T, is extremely high, maybe millions of Kelvin?
So if T is the factor that weights the importance of energy versus the importance of entropy, what happens when T is astronomically large? Does that extreme heat make the energy component, the U or the H, almost completely irrelevant?
If T is, say, a million Kelvin, that minus TS term becomes absolutely enormous.
Yeah.
So in those environments, is the system's entire existence just a race toward maximal S, maximal disorder, regardless of what chemical or even nuclear bonds need to be broken?
It raises this provocative thought that at the very highest temperatures, all physical structure breaks down, not just because the kinetic energy is high, but because the dominance of that T factor in the thermodynamic potentials drives the system entirely and exclusively toward maximizing the log of omega,
Resulting in absolute universal disorder.
The arrow of time becomes the only mandate left. It strips away all other considerations of order and bonding. It's something to mull over the next time you watch an ice cube melt.
A fantastic, truly deep note to end on. Thank you for guiding us through the chaos and the order of probability today.